Hello, this is Mr. Best. Welcome to Chapter 8, Polygons and Circles. This is Lesson 8.3.3, Day 2. Question 123. The city of Denver wants to help build a dog park. The design of the park is a rectangle with two semicircular ends. Note, a semicircle is half of a circle. You got a little diagram over to the right here. A, the entire park needs to be covered with grass. If grass is sold by the square foot, how much grass should you order? All right, so we have the two semicircles, which would actually create one full circle. So you can find the area of the circle, and then you can find the area of the rectangle to figure out how much we need to cover in terms of the grass. So we have 30 feet up into this point, so that's the radius of the circle. And so then this total distance is 60 feet by 55 feet. So we can find the area of the rectangle. That would be equal to 60 times 55. So therefore the area of the rectangle is equal to 3,300 square feet. And now we need the area of the circle, which is pi r squared. So pi r is 30, so 30 squared. And remember, we are finding the area of an entire circle because you have half here and half here. So therefore the area of the circle then will be 900 pi. And then we can add those two up to figure out the area. And when you add them up, we'll just approximate it. So you can put 900 pi into the calculator plus the 3,300. And you'll approximately get 6,127.4. And then this would be in square feet. So let me write this: 6,127.4 square feet. And it says if grass is sold by the square foot, how much grass should be ordered? That's how much grass should be ordered to cover the field. Now in part B, it says the park also needs a fence for its perimeter. A sturdy chain link fence costs about $8 per foot. How much will a fence for the entire park cost? So now we're looking for the perimeter. So we have 55 here, 55 here, and then once again, half of a circle will create the full circle circumference. So we have the rectangle, which is just going to be 55 plus 55 plus circumference is 2 pi r, so 2 pi times the radius. So this would be 110 plus 60 pi. So the perimeter would equal, once again, approximately 110 plus 60 pi. And that would be approximately 298. We'll go with 0.5, and that would be feet. So that's the perimeter. But it wants to know how much it's going to cost, and it's $8 per foot. So then you'll take this and you'll multiply it by 8 for the square foot, and then that means you'll have a total cost of $2,387.96. So for part B, the total cost for the fence will be $2,387, round to the nearest cent would be 96 cents. On to part C. The local design board has rejected the plan because it was too small. Big dogs need lots of room to run. The president of the board said, therefore, you need to increase the size of the park with a linear scale factor of 2. What is the area of the new design, and what is the perimeter? Well, by a scale factor of 2, the perimeter is just going to double. So if the perimeter was, where was it at? 298.5 feet, and then you just double that, then that will be your new perimeter of approximately 597 feet for the perimeter. Remember, if your R has a linear scale factor of 2, then your area is going to be squared, so that would be 4. So now we're going to take the area, which was approximately, let's go back to the top there, 6,127.4 feet squared, and we'll multiply that by 4, which will give us an area of the new park to be approximately 24,509.6 square feet. So there's the area for the new park, and then the perimeter for the new park. Question 124. This problem is a checkpoint for angle relationships in geometric figures. It will be referred to as checkpoint 8. Once again, reminder that checkpoints are things that we should hopefully at this point have mastered. So let's see what we can do. For each diagram, solve for the variable and name the relationship used. So in part A, we have a straight angle, which are supplementary. So 4x minus 3 plus 3x plus 1 is equal to 180 degrees. That's 7x minus 2. Add 2 to the other side, and then divide by 7. So x is equal to 26 degrees, and once again, the angle relationship these are supplementary angles because they're straight angles. Part B, we have two parallel lines cut by transversal. So this angle here is congruent to this angle because those are corresponding angles. And then that angle is congruent to this one. So this angle right here is 5x plus 6 because they're congruent. And then those two angles are vertical. So they're congruent as well, which means their measures are the same. So we should be able to say 5x plus 6 is equal to 2x plus 21. Subtract 2x, subtract 6, divide by 3, and x is equal to 5 degrees. And this is really a combination of, really, you could look at it a couple of different ways, but the way I looked at it was corresponding angles, and then I also looked at vertical angles. So corresponding angles were congruent, and then vertical angles were congruent. Next, C, we have the three angles of a triangle. So we know that the triangle angle sum theorem states that all three angles have to add up to 180. 4x plus 28 degrees plus x plus 19 degrees plus 3x plus 13 degrees is equal to the sum of 180 degrees. Once again, that's the triangle angle sum theorem. So we add them up. 4x plus x plus 3x is 8x. And then 28 plus 19 plus 13 is 60. Subtract 60 to both sides, divide by 8, and x is equal to 15 degrees. And then on to part D. This one we have a triangle again, so we have a right triangle. This angle right here is 40. If we need this angle, this is 50, because once again the sum of the angles of the triangle. And then also these two angles are they're straight angles, so which means they're supplementary. So I could say that those two angles are supplementary. The other thing is, if you remember the exterior angle, so this is your exterior angle right here, it's equal to the sum of the remote interior angles. So this is equal to, so these are our remote interior angles for that exterior angle, so you could also set it up that way. But either way, you will get that, 4x, you could set it up as 4x minus 10 degrees is equal to the sum of 40 degrees plus 90 degrees. And so that's 4x is equal to 130, add 10, so that's 140, and then divide by 14, or divide by 4, sorry. And x would be equal to 35. And so that's if we use the exterior angle. Otherwise, we could have set it up and just said 50 degrees plus 4x minus 10 degrees is equal to 180. And you would get 4x is equal to 40, subtract the 40, you still get 140. So you're still going to get 35, but just another way to look at it. So either way is fine. Question 125. Line segment BE is the mid segment of triangle ACD. So BE is the mid segment, so that means this side length is equal to this one. And then this one is equal to this one. Find the perimeter of triangle ACD. So let's start there. If this is 6, then this has to be 6 down here, ED, and then BC has to be 7. 11 is the smaller triangle, and since the lengths are doubling, so AE to ED, 6 to 12, 11 then means that CD would be 22. So the perimeter of triangle ACD would be 7 plus 7, 6 plus 6, and then plus your 22. So the perimeter is equal to 48 units. If the area of triangle ABE, which is this one right here, is 19 centimeters squared, what is the area of triangle ACD, which would be the bigger one? Since the linear scale factor is 2, then the area, so if r is equal to 2, then r squared is equal to 4, so then therefore I should be able to take the area of the smaller triangle and multiply it by 4 and get an area of 76. And so therefore the area of triangle ACD is equal to 76 square units. Question 126. Chrissy has tied a string that is 24 centimeters long into a closed loop, like the one at the right. Part A. She decided to form an equilateral triangle with her string. What is the area of the triangle? Alright, so since it's equilateral and it's 24 centimeters long, then we have to divide that by 3 so that all the side lengths are the same. So we're going to have a triangle that has side lengths of 8. And we're trying to figure out what the area of this triangle is. So we need the height of the triangle. And since it's equilateral, then we know all the side lengths all the angles, are 60 degrees. So this would be a 30, 60, 90, which we could use our special right triangles. So we know that each of these side lengths right here would be half of 8, which would be 4. And then the long leg is the short leg times the square root of 3. So 4 square roots of 3. So to find the area, we would want to take 1/2 times the base, which is 8, times the height, and that would be 4 square roots of 3. So the exact value would be 16 square roots of 3. And then if we approximate 16 square roots of 3, that's about 27.71, and it is centimeters, so this would be centimeters squared. Part B, she then forms a square with the same loop of string. What is the area of the square? Is it more or less than the equilateral triangle she created in Part A? So now, since it's 4 sides and it is a square, all the sides have to be the same. So once again, on this one though, we're going to take 24 centimeters and divide by 4 parts, which makes each side length 6 centimeters. So 6, 6, and so on. And so to find the area, we take 6 times 6, or 6 squared, and that's 36 centimeters squared. And so you can tell, which one has more than, is it more or less than the equilateral? Well, 36 is bigger than 27, so the square has, more area than the equilateral triangle. All right, on to part C. If she forms a regular hexagon with her string, what would its area be? Compare this with the areas of the square and the equilateral triangle. So now we're going to go a hexagon, so 6 sides. So now we'll take 24 centimeters and divide by 6 different sides. So each side is 4 centimeters. So if we think of our hexagon, something like that, then we create this triangle, and this has a length of 4. So I'm going to make that a little bit bigger so we can kind of put the pieces in. So we need to find the area of this. And so if the base is 4, with this being isosceles, this length and this length are both 2. Now we got to figure out some of the other parts, which we also need to know the angle. So remember, one way we can do this is this whole middle part is 360. So if we divide that by 60, that gives us an angle of 60 degrees right there, but then half of that is 30, so we're looking at another 30, 60, 90 with the hexagon. And so the short side is 2, the hypotenuse, not that we need it, would be 4, and then the long leg would be the short leg times the square of 3, which is 2 square roots of 3. So the area of this triangle, one of the 6 triangles, is 1/2 times the base, which is 4, times the height, and that's 2 square roots of 3. So the area of that triangle would be 4 square roots of 3. Half of 4 is 2, 2 times 2 is 4, so 4 square roots of 3. But there's 6 different triangles in a hexagon, or 6 same triangles. So then we can take 6 times 4 square roots of 3, which would be 24 square roots of 3 in terms of the area. So the area of the hexagon would be approximately 24 times the square root of 3, and that is 41.57. So 41.57, and then once again, this is in centimeters squared. And so once again, comparing that to the other two, it's gotten even larger. So the regular hexagon is even more of an area. On part B, it says, what shape would Christie form to enclose the greatest area? Well, if you kind of follow along with what we've done so far, we went from a triangle, 3-sided, to a square, 4-sided, to a hexagon, regular hexagon, 6-sided. So it seems like the more sides that we create, the larger the area would be. And so in this case, if we keep going, and we keep adding sides and basically get to infinity, then it appears that the circle would have the largest area. And so kind of a bonus part I decided to go ahead and do is kind of show you what the area that would be then. Since we know that a circle, if we use the shoestring and we go all the way around, which would be the circumference, is 24 centimeters, then I went ahead and said 24 is equal to 2 pi r. You can divide by 2 pi to figure out what r is, and then you can replace r with 12 divided by pi in terms of the area, and I came up with an area approximately 45.84 centimeters squared, which once again is larger than the hexagon. Question 127. 3 spinners are shown at the right. If each spinner is randomly spun, and if spinners number 2 and number 3 are each equally divided, find the following probabilities. So if we're looking at the 3 spinners, B would be a quarter of the circle, A is 3/4, C is a half, D is a half, and then it's broken up into 3 parts here, so they're all the same. We have 1/3, 1/3, and 1/3. So the probability has been an A, C, and then an E. So A is 3/4, and then it's been a C is a half, so we can multiply that by a half, and then E is a third, so we can multiply that by a third, and then that gives us a probability of 3/24, which would reduce to 1/8. So that would be the probability of spinning an A, a C, and then an E. On B, spinning at least one vowel. So I went ahead and set up the tree diagram, and then we can figure out what the probability of spinning the at least one vowel. So once you spin the A, you're good. So all of these other 6, whether it's A, D, F, or A, C, E, all of these 6 are going to work. So if you look at your probabilities, 3/4, 1/2, and 1/3, and you multiply that, then you're going to get, where are we at, 3/24, and those will all be the same because they're all getting 3/4 times 1/2 times 1/3. So you'll get a total of 6 of those same probabilities. Now, any of those will work because you'll spin a vowel on that very first one. So if you add all those up, there's a total of 6. That'd be 18/24. So just by spinning the A in the beginning, your probability has gone up a ton. Now on the next one, when you spin a B, then you spin a C or a D, so none of these matter because you're not getting a vowel. So when are you going to finally get that first vowel? It's either going to happen right here or it's going to happen right here. So that's 1/4 times 1/2 times 1/3, which is going to be 1/24. And then the same thing down here will also be 1/24. So we'll go ahead and add those two to our probability. And then that would give us 20 out of 24, which if you reduce that by 4, that would be 5/6. So 5/6 will be the probability of spinning at least one vowel. And you can also see on the tree diagram, in terms of part A, when we answered that, you have, if I spin an A, then a C, and then an E, so 3/4 times 1/2 times 1/3. So that's also on the tree diagram if that's helpful. Question 128. The isoperimetric theorem states that all closed figures on a flat surface with the same perimeter, the circle has the greatest area. Use this fact to answer the questions below. What is the greatest area that can be enclosed by a loop of string that is 24 centimeters long? Well, not realizing this question was going to happen, if you go back to my previous problem on question 126, you notice that last part of D, I went beyond and I kind of showed you what the area would be. So this really answers question 128. So let's go back to that slide and we'll kind of put it over here as well. So on part A, what is the greatest area that can be enclosed by a loop of string that is 24 centimeters long? Well, since we know it's a circle, for sure now, there's the circle. We're able to use the circumference 24 to figure out what the radius would be and then plug that into the area. Part B, what is the greatest area that can be enclosed by a loop of string that is 18 pi centimeters long? So now we're saying that the what's the greatest area? So now the circumference on this one would be 18 pi. So therefore, circumference is 2 pi r is equal to 18 pi. So to solve for r, we can divide by 2 pi. 18 pi divided by 2 pi gives a radius of 9. So the area is equal to pi r squared, with r being 9. So the area would be 81 pi. And that would give us an area of approximately 254.5. And this will be in centimeters squared. Question 129, multiple choice. The diagram below, or shown at the right here, is not drawn to scale. If triangle ABC is similar to triangle KLM, find KM. So BC, this side length right here, matches up with LM. And we know this for sure because right here, BC and LM are in those same positions when they do their similarity statement. So I'm going to do 6 over 9 is equal to, and now let's pick this length CA. So that's 9. And then CA should match up with KM, which I'm going to call X because we don't have that, is then equal to, let's do this length right here. We'll call this Y is equal to Y. And then BA matches up with KL, and KL is 9. So the diagram below, once again, not drawn to scale. We are trying to find KM, and KM in my scenario over here I said was X, so we'll use this expression to solve. So that will give us 6X is equal to 81. And then you can divide both sides by 6, and you will get a value of 13.5. So Km is equal to 13.5. I do not see 13.5, so maybe we should go back and check. But there is a none of these, and that actually is what it is. It's just not on the multiple choice answer part, but it is 13.5. Once again, similarity, since they are similar, we are able to say that their sides are in proportion.